Hey y'all, it's Miss Welch. I'd like to do a brief discussion of chemistry and basically just an introduction to the primary terminology that you'll need to understand later concepts. So we're going to talk about matter through a discussion of the periodic table and its parts, subatomic particles of atoms as well as atomic number and atomic weight or mass, and then a brief description of ions and isotopes. So let's dive in. I'm sure that you have seen a periodic table like this one before. Remember that a periodic table is a chart of all the elements of matter. Everything's made up of matter, and the smallest subtypes of matter are elements, and the smallest parts of elements are atoms. And so we can use the periodic table to talk about the components of compounds and then larger macromolecules and all the different chemicals that make up your body. If we zoom into the periodic table, let's just focus on one element. Let's just focus on carbon here. And then we can look at all the different properties of carbon. So first you have that big letter C, and that letter C is its atomic symbol. And that symbol or letter, and sometimes it's two letters, right, on some of the other ones, that atomic symbol is how we identify that element in a compound or a reaction or a molecule. So carbon's atomic symbol is a C, and then you see this big number 6. Now some periodic tables have that number in different place in the box, but it'll usually be the largest number in the box, and that's its atomic number. And the atomic number stands for how many protons are in each atom of carbon. So we're going to look at protons a little bit later in just a minute. The number under carbon here is a 12. So we're not going to worry about any of this other stuff. But this number under carbon is 12 point ... something. That is the atomic weight or the atomic mass. Now, you may see those terms interchangeably because they're pretty much equivalent on Earth, right? Weight is the mass of an object as it depends on the gravity, on the gravitational pull of that object. So our mass would be the same on the moon, but our weight would be different because of a difference in gravity. So sometimes here on Earth you hear atomic mass and weight interchangeably, particularly in biology. We don't usually talk about the biology of the moon. So you can use either one of those terms for most purposes. But the atomic mass is 12 with some rounding in there. And that is the number of neutrons and protons put together because that's their weight. That's how much mass those particles take up in each atom of carbon. Now, the periodic table has over 100 elements on it, and so for biology, anatomy, physiology, living things, we're not worried about every one of them because some of those are not naturally occurring or they're occurring in very small quantities. So you can look at this picture here and see some of the elements that make up the majority of our bodies. So oxygen's number 1. Think about all that water in your body, H2O. And then, of course, the hydrogen, and then carbon. We know we're carbon-based molecule, carbon-based organisms. And then other ones like nitrogen, phosphorus, sulfur, continuing down the line. So you can remember that by CHNOPS. That's a good way to remember it. Carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. That's the first, basically pretty close to the first 6 most common elements in living organisms. This is a stylized drawing of an atom. Now, even though atoms are super tiny, they do have their own subparticles, subatomic particles. And so you've heard of these before. Protons and neutrons are in the nucleus or the center, and electrons are around it. Now, we say these are in orbits or electron shells. Now, let's talk about the weight of the atom itself. Adding up the particles would equal the weight, right? You have to add up all the pieces. The way that we measure these are in atomic mass units. Now, they're so tiny and so little mass that we figured out that one proton has a weight of 1.6 times 10 to the negative 27th kilograms. That's 27 zeros after the decimal point. So it's super tiny. So to make it easier to add and understand and calculate, we just call that 1. We say one of those equals that decimal number. So we measure them in atomic mass units just as an easier method of measuring. So a proton equals 1 atomic mass unit. A neutron does too. So neutrons weigh 1 atomic mass unit. Electrons are so much even smaller than that they don't register on the scale. So we say they're 0. They don't weigh enough to even register with the protons and neutrons. So if you're looking at weights, we say protons and neutrons have all the weight, the atomic mass or atomic weight in the center, 1 for each one, and then electrons have 0. Talk about charge now. Each of the particles has an electrical charge. The protons in the center have a positive charge, the electrons have a negative charge, and the neutrons are neutral. They don't have a charge at all. So think about that with the arrangement of these. Negative and positive are attracted to each other. So the protons and electrons are attracted to each other, and that's why the electrons are staying close. However, an electron and another electron are both negative, so they would repel each other. They would not want to be close by. So they are circling around the positives, trying to stay close to the positives, but trying to stay away from each other. So let's talk about how all that information relates to ions and isotopes. So 2 isotopes are the same element, but they have different weights. So if you look at this picture here, we're going to talk about hydrogen and its different isotopes. So as you can see, we have H, H, H. They all say hydrogen. We've got little different nicknames for them, but they're all hydrogen. They'll have 1 electron, that's the blue in the outside circle, and then they have 1 proton, that's the green in the center. So they all have that same setup. The first one, protium, has no neutrons in the center, nothing extra. So it weighs 1, right? Protons weigh 1 atomic mass unit. Now, deuterium has a proton and it has a neutron, so it weighs 2. And a tritium has a proton and 2 neutrons, so it weighs 3. So all we've changed is the neutrons. The protons are what decides an element. That gives its identity, it gives its abilities and chemical reactivity. So it has to stay the same to be the same element. However, the neutrons can make it heavier and cause it to have different isotopes. So I think about it like a person, right? No matter whether, if this is my normal in the middle, if I lose some weight or I gain some weight, I'm still me. I'm the same person. And so elements have the same feature, and we call those isotopes. This is why on the periodic table, when we looked at carbon, it had that 12 dot and had a decimal after it as the atomic mass or atomic weight of carbon. There are several isotopes of carbon. The one that's 12, weight 12, with 6 protons and 6 neutrons is the most common in nature. However, there are carbon 13 and carbon 14 isotopes, and so that will change the weight. And so that weight on the periodic table is a percentage of all the naturally occurring isotopes combined. So because there are 13 and 14 isotopes, the average weight is a little higher than 12, but 12 is the most common. Usually for our purposes, we just round it to the nearest number, especially in biology. Those isotopes of carbon are really important in science. That's how we get carbon dating. We talk about radiometric dating of fossils. That's because we're measuring the difference in carbon 12 and carbon 14 from the fossils. We also use isotopes because they can be radioactive in medicine. Think about imaging, like for your thyroid. We can use isotopes of iodine to measure the uptake of iodine in your thyroid and measure that on different imaging scans. Now, to talk about ions, we need to look at those electron orbitals or electron shells again. So the electrons circle around the nucleus in rings or in orbits. And as you get away from the center, you can have more electrons circling. They have to have enough space, right? Those negative charges repel each other, and they have to have enough space to stay separate. So if you look at the first couple elements, we'll just look at a couple here, carbon and neon. The smallest ring around the nucleus can only hold 2 electrons because it's so close. They have to stay apart. We can only fit 2 in there. So you have 1, 2, and you look in this one, 1, 2 on that center ring around the nucleus. So the first shell can only have 2. Now after that, for most of the biology important molecules, we can have 8 in the next one. We call it the octet rule, that the rings can hold 8, and that will make the atom happy. That will make it full and inert. It won't react if it has 8 because it's done. It's happy at that number of electrons. Now, carbon, if you remember, has 6 protons, so it has 6 electrons when it's stable and neutral. So if you put 2 in the first ring, you can put 4 in the second ring. And that would be it, right? 1, 2, 3, 4, 5, 6. That's how many electrons it has. Now that's not 8. That's only 4 in the outside. So carbon would love to have 4 more electrons to make it stable. This is why carbon is such a fabulous molecule to be made of, because it needs 4 more, so we can add 4 more different things by bonding, which will be in another discussion, but that's how we get bonds, because we're trying to fill those extra spaces. Look at neon. Neon has 2 in the center, and then 1, 2, 3, 4, 5, 6, 7, 8 in the outside. Wow, it's already full, so neon is inert. It does not react easily with other elements because it's already happy as it is. You can't get it to change because it is full of its maximum number of electrons. This outer ring, no matter how many rings it has, the outer ring is always called the valence electrons. Those are the outermost ones. Those are the only ones that can react in reactions to make bonds, are the outside ones. The inside ones are stuck. You don't react with those. Let's look at an element like sodium. So sodium's symbol is Na, and it has 2 electrons in the first ring and 8 in the second, and just 1 in the outermost ring. It has to have a third ring to get that last electron in. So this is a very reactive element. That 1 negative charge in that electron is kind of messing up the vibe here. It would rather have 8 and be full and be inert. So this element, this atom, can become an ion. An ion is either a positively or negatively charged particle. So sodium can give up this electron, so it's giving away a negative. So if you give away a negative, you're more positive. So sodium, we say, as an ion, can have a +1 charge. It can have a little positive charge because it gets rid of this 1 electron. Now its valence shell is 8, and that makes it more stable. We call ions with a positive charge, like sodium would make, a cation. C-A-T-I-O-N, cation. All right, let's look at a different element. Let's look at chlorine. So chlorine is Cl, and we're back to 2 in the center ring, right? 8 electrons in the next one, and in the outer ring, 1, 2, 3, 4, 5, 6, 7. Oh, we're missing 1. So chlorine normally has 7 electrons in its outer ring. And man, wouldn't chlorine love to have an extra to fill that up and be whole and be complete and have 8 valence electrons? Of course it would. So if chlorine can beg somebody into giving it an extra electron, it would add a negative charge. And so that would make this an ion that is slightly negative, a -1 charge, because it has an extra electron to fill its outermost valence. So an ion that has an extra negative charge, 1 or more, would be called an anion, A-N-I-O-N. Now we're going to see that these ions are going to be really important in making bonds. So you could already guess, right, that if one thing likes to give up a charge and one thing likes to gain a charge, right, those electrons, then they're going to be best buds. They're going to make bonds. So this electronegativity, the valence electrons in each of the elements, all are going to be super important for making chemical reactions and chemical bonds. All right, that's a brief overview of the important terminology to get started in biochemistry, like the atomic number, atomic weight, the subatomic particles, and ions and isotopes. So a lot of vocabulary. Thanks for watching.